Hey everybody, welcome to another edition of Cosmology, pre-recorded on the internet. We have finally finished up talking about the cosmic microwave background, and we're ready to get into primordial or Big Bang nucleosynthesis. So this lecture, which is hopefully going to be less than a half an hour, is going to give you a sort of 30,000 foot view of what Big Bang nucleosynthesis is all about. So, what I'd like to do is start out with I guess, discussion of what we learned so far about the time, temperature, and energy evolution of the universe. So, if you recall, we can talk about how the universe has evolved with redshift if you want. So let's let time run from left to right, but that means we're going to let redshift run from right to left. Can I try that one more time? Oh yeah. Okay, so this will be redshift z. And of course, today the redshift is 0, right? Light emitted today and observed today has a redshift of 0. This is not going to be a linear scale, but it's worth pointing out some things that some significant redshifts that have happened along the way. So at a redshift of about 0.31, relatively recent in redshift, but of course this still corresponds to several billion years ago. At a redshift of about 0.3 or so, that's when dark energy started to dominate, dark energy domination, at least in the model, the simplest model, which is that of a cosmological constant. And there's sort of a period at redshifts a bit larger. We talked about discovering or measuring supernovae fluxes at redshifts of perhaps 1 or so. And we talked about most recently things going on at a redshift of about 1100. So this is maybe 1100 or so. This is when the cosmic microwave background was formed. That is to say, last scattering occurred about then. And I suppose it's also worth pointing out that today the temperature of the universe, at least determined by the cosmic microwave background, is approximately 3 Kelvin. And at the time that the CMB formed, which was about, when the universe was 1,000 times smaller, that temperature was about 1,000 times bigger. In other words, about 3,000 Kelvin. And in between, interesting stuff happened, right? We had something called, after the cosmic microwave background formed, last scattering, there was the so-called dark ages where, structure was growing, but nothing interesting was going on. There were no planets, no stars, no nothing. Not dark energy, dark ages. Followed by eventually the first stars turned on, and when that happened, you again had high energy photons streaming through the universe, and that did what's called reionization. It reionized the neutral hydrogen to make ionized hydrogen. At least some fraction of it was reionized. So dark ages, reionization, and then of course structure formation, the formation of the first stars, and later stars and solar systems and stuff. Okay. But that being said, the cosmic microwave background has information on it from what was going on at the time the cosmic microwave background was formed, but it also might contain information, what people hope anyway, about things that were happening before it was formed. That is to say, one example would be primordial gravitational waves may have been produced by early universe physics, like inflation, for example. And if that's true, then they may have left a pattern in that cosmic microwave background, and that's one of the most interesting things people are looking for in the CMB, cosmic microwave background polarization. And specifically, they're called B modes in the polarization of the cosmic microwave background. But I guess the main thing I want to point out is that we can see things back until about a redshift of 1100, but everything earlier to that is opaque to us. I hope I've spelled opaque correctly. You never know with me. And the question is, in addition to what patterns might be on the CMB, is there any other information that we can glean about what was going on during the early universe? Any other information that supports this Big Bang model that we have? And one thing you might start thinking about is, at higher redshifts, the temperature should get higher as well, and eventually the temperature and the energies should get high enough that at some point nuclear reactions were going on in the hot, dense universe. So, for example, at a redshift not of 1,000, but let's say a redshift of about a billion, 10 to the 9, the temperatures would be 10 to the 6 times higher than they were during the cosmic microwave background. That would mean temperatures on the order of 10 to the, I'm not going to do this right, 3 times 10 to the 9 Kelvin. Those would correspond to energies like, for example, the average photon energy would start to be on the order of 1 mega electron volt, which is the scale of nuclear reactions. So I want to go ahead and show you a picture that we will try to justify. This is, you'll see many different graphics about what has happened in the universe, but at least this will kind of be a little bit more detail of what I was just showing you screen right. So, today at roughly 14 billion years after the Big Bang, that's where we are. Dark energy started to dominate here. Going back to where the CMB was formed, that's here. And, even earlier was when finally radiation started becoming less important. Matter started dominating. That occurred about 50,000 years after the Big Bang at a redshift of about 3,600. But much earlier on, we're talking not years or even months or days, but minutes after the Big Bang. That's when primordial nucleosynthesis occurred, and that's what this whole chapter is about. At earlier times, at even higher energies, there were other things that presumably occurred. The quark-hadron phase transition, the QCD phase transition of the early universe, that's of energy scales that are of order several hundred MeV. Earlier than that, there should have been, according to our well-tested theory of the electroweak interaction, there may have also been an electroweak transition. And I would say that this is all good stuff that you might certainly believe predictions that are made up to times about that early. Things that are even earlier at higher energies higher than several hundred GeV, are not that well tested, or perhaps not even tested by our modern particle accelerators. So things to do with supersymmetry or axions or anything earlier, like grand unification or quantum gravity, we have no experimental evidence for whatsoever. So those are, if you like, I think I could fairly say a bit more speculative. Okay, that being said, let's talk about nuclear interactions. You may already be familiar with the fact that it's nuclear interactions responsible for almost all the life on Earth. That's because, of course, the way that the sun is fueled, it's fueled by fusion reactions going on in the core. So, nuclear reactions. Something that you might be interested in the sun. Oh, my handwriting is terrible. Sorry. For example, the so-called, what is it called? The PP chain. But anyway, in the sun is mostly hydrogen. What happens is you've got a proton and a proton coming in. They would Coulomb repel, but because of quantum physics, they have a finite probability to, tunnel through their own barrier. And in the process, it is energetically favorable to produce a so-called deuterium nucleus, plus an anti-electron or positron, plus an electron antineutrino. You might also write this in the sort of nuclear notation. A proton, which is just an ionized hydrogen atom, turns into a deuterium, which is a proton and neutron stuck together. You might call that 2H, plus the positron, plus the antineutrino. Now, in the process, there's actually also excess energy that is created. This is a so-called exothermic reaction. For it to be energetically favorable, it would have to do that, plus about an MeV, or about 0.93 is what I calculated, of kinetic energy, which is shared between the different particles, but primarily goes into the positron and the antineutrino. So this kind of reaction occurs in the sun, and you can see that the energy scales involved are of order MeV. This reaction can't occur in the early universe. It just simply wouldn't happen with high enough probability. But what can occur in the early universe early universe type of reaction would be something like this. A proton and a neutron come together because at early enough times there are free neutrons floating around, and this could form a deuterium. And also an exothermic reaction, it emits a photon is emitted in the process, where the photon energy is called the binding energy of deuterium. I'm going to call it Q, and this has a value of about 2.2 MeV. Again, the scale is mega electron volts. Q is called the binding energy, and one way to see that is thinking about this the other way. The deuteron, a proton and neutron together, requires a photon, or if you like, a photon comes in and hits it with an energy greater than or equal to 2.2 MeV, and that will so-called photodissociate the deuteron. So example, photon energy greater than or equal to 2.2 MeV can, I don't need to use quotes, that's what it's called, photodissociate. This is in some way the analog to ionizing an atom, but here we're not talking about atomic physics where the energy scales are of order eV, we're talking about nuclear scales where the energy scales are of order MeV, or about a million times greater. Okay, so that's what we've got. And in fact, so now we're talking about protons, neutrons, we're talking about deuterium. Let's go ahead and list the cast of characters that you might be interested in, and we will be interested in, as we study what goes on in the early universe with this production of really the light elements. So there are several isotopes to consider. Isotopes. And we've seen some of them. You've got a proton and a deuteron, deuterium, and there's also something called a triton or tritium atom. And you can also list these as the 1H, right, which is just a proton, 2H, which is a proton and a neutron, and tritium is one proton and two neutrons. And that would, you could write that like this. So if you like, these are all the objects which have a charge of 1e. There's also things that have two charges. That would be helium-3 and helium-4. Going up the list, thinking about what the periodic table looks like, you've got lithium. Turns out that the stable isotopes of lithium are pseudo-stable. Lithium-6 and lithium-7. And then we've also got beryllium, beryllium-7, beryllium-9, and beryllium-10. So these are some of the major players when one goes to carefully analyze what goes on during Big Bang nucleosynthesis. This is also a good opportunity to talk about something that is motivated by the fact I have not written down beryllium-8, and you may wonder why. So it turns out beryllium-8 is something that can be produced in the lab, but decays incredibly quickly. So no beryllium-8. Why? Because the decay time, it's an unstable particle, the decay time for beryllium-8, I'll write this as decay time for Be8, is approximately 10 to the minus 16 seconds. And the reason why, or one way to see why beryllium-8 is an unstable particle, is that beryllium-8 looks like two helium-4 nuclei stuck together. Basically, beryllium-8 would much rather decay into two heliums plus some extra energy than it would be to stay the way it is. So the way to understand that, though, is in terms of this binding energy. If you were to ask, what's the binding energy of a particular isotope, and divide that binding energy by the number of nucleons in that isotope, again, a nucleon is either a proton or a neutron, then you could make a chart, which I think I need to show you. Maybe I'll sketch it out and show you the better chart. If you were to make a plot as a function of A, where A is the number of nucleons, which is, number of protons plus number of neutrons, and you asked what's the total binding energy. Again, binding energy means the energy required to separate that isotope into all its constituent neutrons and protons. You take that total binding energy and divide it by the total number of nucleons in that isotope, and this will be in units of MeV. Then, roughly speaking, there's this general kind of shape. If you study nuclear physics, you'll see that this has a kind of curve, and it peaks up top here at iron. But at least if we focus on the light elements, and we kind of make this chart 2, 4, 6, 8, something like this, 2, 4, 6, 8. Then what you'll find is at A of about 2, the only isotope there is the deuteron. This has a binding energy per nucleon. It's the 2.2 MeV divided by the 2 nucleons, so it has a binding energy per nucleon of about 1. Going further up the list, helium-3 and the triton. Helium-3 is somewhere over here. Let me call this deuterium. This is helium-3, and then tritium is here. And then you go to 4, and then you've got helium-4 with a very large binding energy per nucleon. In other words, it takes a lot of energy to separate helium-4 into two separate protons and 2 separate neutrons. That's all the way up here. And then you'll find that other things exist. Actually, nothing stable at 5, and at 6 you'll find, for example, lithium-6 is somewhere a bit lower. Basically, if they can, these isotopes want to evolve to the highest binding energy per nucleon they can. It's kind of like a system wants to end up in its lowest energy state. Let's see if I have a better picture to show you. Nuclear processes. So, okay, this is just showing you a picture, for example, what happens when a proton and neutron comes together. You can form this deuterium. In the process, a photon is emitted. If that deuterium then goes along and meets up with a neutron, it can form, therefore, a triton. And if that thing gets bombarded with another proton, that is one way to create a helium-4 nucleus. And there's a series of reactions that occur. This may look complicated and busy, but trust me, there are many more such reactions that need to be taken into account in these sophisticated Big Bang nucleosynthesis codes. But this can show you the different ways that one can take a proton and neutron and combine different light elements to form the heavier light elements like helium, like beryllium, lithium, etc. This is the chart I wanted to show you, though. The average binding energy per nucleon, you can see quite clearly, I hope it's clear, that you've got your deuteron quite low. Helium-4 has this large binding energy per nucleon, and so anyway, it's certainly if you like, it's more stable than some other things which have lower binding energy per nucleon. Right, this is showing lots and lots of elements. Okay, so let's move on then. Again, this is a bird's eye view of what's going on here, and we're going to get into more detail in further lectures. So we might want to know then, okay, the nuclear energy scales are of order MeV. When the universe was young enough and it was compact enough, at high enough redshift, at high enough temperature, it would be high enough energy. When does this actually occur? When does the universe have, let's say, characteristic energy of order MeV? And one way to see that is to use the Friedmann equation, and with some knowledge about how the temperature evolves with redshift or scale factor, we can put this all together. So when does the temperature, when does the average energy, let's put it like that, when does the average energy approximately equal to, let's just put of order 1 MeV? Okay, again, the nuclear scale. When? In time or redshift, etc. So let's do two things, and I'm going to skip some steps and let you fill in the gaps because that's better for you. Let's do one thing. First of all, let's use Friedmann. We're going to use the Friedmann equation, and we're going to use the Friedmann equation at these early times when the universe was radiation dominated. In other words, Hubble parameter squared is equal to whatever the Hubble parameter is today squared, and then there's all these terms that depend on the amount of matter, radiation, etc., but it's radiation dominated, so we should put radiation density parameter today, e to the minus 4, and then plus things that we're going to neglect, or negligible is what I want to say here. Okay, you certainly get to neglect cosmological constant at these times. It is totally subdominant. So that fact plus the fact that the temperature as a function of time is equal to the temperature today divided by the scale factor as a function of time. What that allows you to do is put these together. So let me first of all rewrite the scale factor as the temperature today divided by the temperature back then, and then use these. And let's change colors because we need it. Oh, one additional fact. Sorry, there are 3 things to note. All these should hopefully be not new to you. At the time it's radiation domination, which means that the evolution of the scale factor is nice and simple. So we're in the rad-dominated phase. Remember, I hope you have remembered this, that the scale factor evolves like t to the 1/2, or in other words, you can write this as t over t naught to the power of 1/2. The significance of that is that the Hubble parameter at that time is given by a dot over a, and it's quite simple to verify that this is equal to 1 over 2t, where t is the time since the Big Bang. Assuming that the Big Bang, right, that it was radiation domination all the way back to the time of the Big Bang. Well, so there's a little bit of a caveat there. But let's put all these facts together. What this apparently means, on the left-hand side, Hubble squared is apparently 1 over 2t squared. This is equal to the Hubble rate today squared times omega radiation today, and then instead of a to the minus 4, I'll write this as t over t naught to the power of 4. Is that what's consistent with my notes? It is. Good. Good. Now we're ready to solve for the temperature as a function of time. Apparently, this means that the temperature as a function of time, verify this please, is equal to the temperature today divided by the omega radiation naught to the power of 1/4. And then you can put this all over the square root of 2h naught over t. And I think the important thing to take away from this in terms of the scaling, notice that the temperature as a function of time, at least back then, goes inversely proportional to the square root of the time. I say that right? The temperature is inversely proportional to the square root of the time. I'll let you plug in these numbers. The radiation density parameter today is on the order of, let's just get order of magnitude, 10 to the minus 4. You can check that in Ryden. The Hubble parameter today is approximately 2 times 10 to the minus 18 inverse seconds, again, order of magnitude. And the temperature today is approximately 2.7 Kelvin or 3 Kelvin if you want to round it up. Now, I'm not telling you what time, but you might want to use, in fact, you should use t, little t, equal to 1 second as a reference value, and then we can see how the temperature would evolve accordingly. So use this and use t equal to 1 second as a reference. I claim that when you put all this together, you'll find that the temperature at whatever time, early times, was approximately equal to 10 to the 10 Kelvin times, and then you'll have 1 second divided by t to the square root. Like if you put in, let little t be 1 second, get that number, you'll find about 10 to the 10 Kelvin. That means that the scaling with time, scaling of the temperature with time goes like this, and this is something that Ryden has in the book. And then one more point here is to get the energies, the scale of the energies at the time, right? It's like there's some small numerical factor times kBt. This is of order kBt, in other words. So this is of order 1 MeV times 1 second over the time. Okay, and just to verify that, you can let kb, at least the order of magnitude, right? It's 8.61 or something, but you let this be approximately 10 to the minus 4 electron volts per Kelvin. That's how you can verify that, okay? So that tells you that the energy scale at which the nuclear processes should be going on, the MeV energy scale, is happening at a time of about 1 second after the Big Bang, at temperatures of about 10 to the 10 Kelvin. Let's see if there's any pretty pictures to show you. Okay, I guess that's it for now. The last part of this lecture then is to talk about Big Bang nucleosynthesis in a nutshell. We're going to get into the nitty-gritty in the couple coming videos, but I want to at least paint a sort of timeline for you. We'll get to that in a moment. So let me write that as BBN timeline. So roughly speaking, what you've got in the early universe, the energies are very, very high, and neutrons and protons, electrons and neutrinos are all talking to each other. They're colliding, interacting very, very rapidly, much faster than the relevant rate at the time, the only relevant rate for these kinds of calculations, which is the Hubble rate. So basically, early times, you have the weak interaction. It's the weak interaction that governs this interactions between electrons, neutrinos, and neutron, proton, etc. Early times, the weak interaction rate. That's the weak strong force. The weak nuclear force. I'll write this once. Weak nuclear force. Weak nuclear interaction. Rates are much bigger than the Hubble parameter, and that means that you end up with, or you have, chemical equilibrium between various species. This means that, for example, a proton and an electron can turn into a neutron and an electron neutrino, but if there is chemical equilibrium, then that means this interaction can very easily go back the other way. Another one, for example, would be a proton and an antineutrino of the electron type can turn into a neutron and an anti-electron or positron, and that is equally likely to go back in so-called chemical equilibrium. Again, chemical equilibrium will be occurring if the interaction rates are high enough. But eventually, you're right, the universe is expanding, it's getting colder, and these weak interaction rates strongly depend on energy, and eventually they cannot occur at a fast enough rate to maintain this equilibrium situation. When that happens, when they fall out of equilibrium, that's called weak interaction freeze-out. Eventually, T, the temperature, and the energies, E's, are too small. There are 3 L's in the word small. And you end up with weak freeze-out, weak interaction freeze-out. And at that point, the only remaining weak nuclear interaction that occurs, there's one very important interaction, is the neutron. Then a lone neutron, you probably already know this, perhaps not, a lone neutron is an unstable particle, and it will decay into a proton, an electron, and an electron antineutrino. And this occurs at a relatively long, over a relatively long time. The decay time for the neutron is approximately 880 seconds, which is on the order of 15 minutes. So early universe, weak interaction is making chemical equilibrium between these species. Universe gets too cold, no longer happens, and the protons and neutrons are kind of hanging out in some abundance, but the clock is starting to tick. Within 15 minutes, most of the neutrons will have decayed, and it is during this window between 1 second and 15 minutes, really closer to like the first few minutes, is when all the important action happens in producing the light elements. So this is what we have going on. We're racing against the clock. All the while, what we have, so now the weak interactions have frozen out. We're waiting for proton plus neutron to make deuterium, and in the process create a photon. And that's all good, and you'll start, once you've got deuteriums around, deuterons around, then you can start producing those heavier elements, helium-3, helium-4, etc. The problem is at this point, you notice that you've got a high energy photon being created in this process. Well, the problem is that this interaction can go back the other way. So basically, you can't produce too many deuterium. Can't produce enough deuteriums because too many high energy photons. Too many photons with energies that exceed the binding energy of deuterium. This is called the deuterium bottleneck. You're stuck because you have to get through deuterium to make all the other stuff, but you don't have enough of them because the universe is still too damn hot. So I'll write this: deuterium bottleneck. So what you have to then wait for is the universe to expand, to evolve even more. From that 1 second mark, you have to let the universe get cold enough that the number of photons with energies that exceed 2.2 MeV are small enough that finally this reaction can mostly happen in the forward direction. So finally, once the universe is cooled, that happens, by the way, at a temperature not of 10 to the 10 Kelvin, which is when the weak interaction freezes out, but this is more like 10 to the 9 Kelvin, which happens at a time of about 180 seconds, which happens to be about 3 minutes. Finally, your protons and neutrons can go forward to making deuterium primarily in that direction. And once deuterium can be produced in large quantities, that's when you can start producing the other elements. So this can all occur. But what's the big deal? How do we verify this? Well, when you actually run these complicated codes, which in this is kind of showing you what's going on, the weak interaction freezing out really starts with neutrinos decoupling, and then neutrons and protons also decouple, and this happens around the same time that a large amount of electrons and positrons annihilate. But these sophisticated standard Big Bang nucleosynthesis codes will show you how hydrogen, or if you like protons and neutrons, evolve in time, reach this deuterium bottleneck. Once it breaks, you start producing the heavier elements. And the great thing, the amazing thing about all of this is that the predictions for the abundances of these elements depend on, as it shows here down on the bottom axis, the density of ordinary matter relative to photons. In other words, it depends importantly on the baryon to photon ratio, which can be determined, for example, from the CMB. So there's already a prediction that goes into the BBN model. With the model, with the baryon to photon ratio, there are predictions made for how much, what the abundances should be of these primordial, these light elements. And the amazing thing is that, at least for the most part, the primordial abundances, as they've been measured with telescopes, of helium-4 and deuterium are consistent with those observations from the CMB and the nuclear physics models of Big Bang nucleosynthesis.